Flux is the amount of field lines penetrating a given area. If I change the amount of current that is entering into this particular solenoid, the amount of field lines penetrating also is changed. A change in electrical current that is passing through that particular coil is producing a change in the magnetic flux. I2 current flowing in the secondary coil is producing a change in flux in the primary coil. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with electromagnetic induction. And in this class, we will be dealing with what is inductance, or simply what are the properties of inductance and the specialities of induction. So let's get right on to it. So the first topic is self-induction, but before getting on to self-induction, we should know what exactly inductance is. So what is an inductor? What is an inductor and what is inductance? So what exactly is inductance? Imagine that there is an electrical conductor, that is a conductor that allows electric current to pass through that. That particular electrical conductor has a tendency to oppose the incoming electric current. That is, if there is an electrical conductor like this, let's say having the length from A to B, let's say having a length L from A to B, if that particular conductor, that particular electrical conductor has a tendency to oppose the incoming electric current, then we can say that that particular property of that particular material is known as inductance. Or in simple terms, we can say that the tendency of an electrical conductor to oppose the incoming current is known as inductance. How it happens and why this happens will be discussed very shortly, but just know that this particular thing is known as inductance. And the particular component in that circuit that uses or that provides inductance is known as an inductor. That is, in general circuits, if you rip apart some remote or some remote cars or something, you can see coils of wire wound around. So that particular equipment is known as an inductor. You can see it in mixies, grinders, any electrical equipment, there will be an inductor. What is the use and how this happens is going to be discussed right now. So we just learned that the tendency of an electrical conductor to oppose incoming electric current is known as inductance. Now, how is this happening? Why is this particular phenomena occurring in electrical conductors? That is what we are going to take a look at today. And we will be starting with self-induction. So what exactly is self-induction? Imagine that I have a solenoid and through which I am passing a definite amount of electric current. So I have a solenoid which is an electrical conductor. When I pass electric current through this particular electrical conductor, according to inductance, there should be something that opposes this current flow. That is, when electric current is passing through this particular solenoid, it should oppose the incoming electrical current. So how does this happen? Why does this happen? So we know that when current is passing through this particular solenoid, there is obviously electrical field lines and magnetic field lines. We'll be just focusing on the magnetic field lines for now. So there will be a magnetic field line around this particular solenoid. Let's say it will be more focused or more concentrated in the center region. That is, there will be magnetic field lines passing through the bulk of this particular solenoid. Now, what happens if I immediately change the current concentration? That is, right now a steady amount of current is flowing through this particular solenoid. If I immediately switch it off, or if I immediately change the concentration of current, then the amount of current passing through this coil changes and immediately the flux which is linked with this coil changes. Because we know that the magnetic field concentration will change if I change the amount of current that is passing through this particular coil. That is, if I provide more current, the field will be more strong. If no current is provided, the field will be very weak, or the field will be non-existing. The point is that as I change the amount of current that is passing through this particular coil, the field also changes. So there is a change in field, or more precisely I can say that the number of field lines passing through a particular area in here is changing. That is known as a change in flux. Again, when we remember the definition of electric flux or magnetic flux, we know that it is the number of field lines passing through a given area. So, number of field lines passing through or penetrating a given area is known as magnetic flux or electrical flux. In this case, it is magnetic flux indicated by phi B. And the equation is B dot A or simply BA cos theta. Anyways, so we know that flux is the amount of field lines penetrating a given area. If I change the amount of current that is entering into this particular solenoid, the amount of field lines penetrating also is changed. If I am allowing current flow into this particular circuit, let's say 1, 2, 3, 4 field lines are penetrating a given area. If I turned it off suddenly, then the amount of field lines penetrating is decreased to 0. There is a change in number. So this particular change in magnetic field lines is going to produce a change in flux, because the number of magnetic field lines will determine the strength of the magnetic field. That is, if I'm changing the current, I'm changing the magnetic field strength, which is in turn causing a change in flux. So what I'm trying to say is that if I'm changing the amount of current that is passing through this particular coil, then what happens? Then there is a change in magnetic field strength, or number of magnetic field lines is changing. So magnetic field strength is changing, which means it is producing a change in magnetic flux. So flux is also changing, which will in turn produce a change in voltage also, or a voltage is developed, or we can simply say that an EMF is actually developed. But for now, just understand this much, that when there is a change in current, then that produces a change in magnetic field strength, which produces a change in flux. Or I can say that a change in electrical current that is passing through that particular coil is producing a change in the magnetic flux. So I can say that current is directly proportional to phi B, that is magnetic flux linked with that particular coil. Because if I change the current, that is if I increase the current, flux density will also increase. If I decrease the current, that is if I turn off the current that is passing through this particular coil, then flux density will go down to 0. So it is proportionally changing. So I can say that current is directly proportional to magnetic flux linked with that particular coil. So here we know that I is directly proportional to phi B, but this is a proportionality sign. So in order to avoid that particular proportionality sign, we need a constant of proportionality, and that particular constant is known as self-inductance or self-inductance constant. So we can say that Li will be equal to phi B, where L is the constant known as self-inductance. So this is the idea behind this particular concept. That is, when we change the amount of current that is passing through a particular electrical conductor, in this case a solenoid, it changes the magnetic flux associated with that particular conductor, which is producing a flux change, that is, it is producing an EMF. That particular phenomena is known as self-induction. And this particular quantity, this particular constant is known as self-inductance. The constant of self-inductance. It is indicated by the capital letter L. And one thing you have to understand is that the unit of inductance is Henry. The unit is Henry. It is to honor a great scientist that we use Henry, but if you want to use SI notations, that is also fine. But just know the unit is Henry, and this is known as self-inductance. When current associated with the coil changes, the magnetic flux associated with that particular coil changes, and an EMF is induced, and this particular phenomena is known as self-induction, and this particular constant is known as self-inductance, constant of self-inductance, and the relation comes from I is directly proportional to phi B. So just now I told you what self-induction is. That is, if I change this particular current, there will be a force trying to oppose that particular change. That is known as self-inductance. In this particular case, if I am changing I, flux associated with that particular coil is changing, which is producing an EMF. That is, when I'm changing current, it is changing the magnetic field, which is changing the magnetic flux associated with that. And we do know that any change in magnetic flux will give rise to EMF. So we do know that it is giving rise to an EMF. Now, in this particular case, we know that induction means it is trying to change or oppose any relative change in the current. That is, if I'm trying to increase this particular current, there will be automatically developing an EMF such that it opposes that particular change. If I'm decreasing this particular current, then the change will be in such a manner that it opposes that relative decrease in current. So just like that, whenever I change this particular current, there will be an EMF developed which tries to oppose that particular change. This is known as self-induction or generally induction principle. And now, what will be the nature of this particular force or particular EMF being produced? So we can say that it opposes change, which means, how do you oppose change? If I'm trying to go this way, if you want to oppose that change, you have to pull me to the other side. If I'm trying to push you, then you have to push me back in the opposite direction. Just like that, if I'm trying to induce current or if I'm trying to put current into the circuit, the current developed should be in such a manner that it opposes that particular relative change. Or to be more clear, we can say that the change in current is inducing an EMF and the nature of that EMF will be such that it opposes relative change. Or we can directly say that E will be equal to, that is EMF will be equal to change in magnetic flux with respect to time, and the change will be in such a manner that it opposes relative change. So this negative sign indicates that the direction is actually in the opposite direction. So now is the reason why this is known as self-inductance. That is, any change in this particular coil, if I change the amount of current passing through this particular coil, then automatically an EMF is being generated in the coil itself. That is, the coil itself is generating an EMF in order to oppose that particular change. That is why it is known as self-induction. And the nature of this EMF is in such a manner that it opposes the relative change. If current is trying to flow through there, then the EMF will be in the opposite direction, trying to say, okay, you can't flow, just stop this. So this relative backwardness, that is, this relative nature of this EMF to oppose the change, because of this particular EMF is known as back EMF. That is, when the current is trying to flow through here, changing and flowing through here, EMF is trying to oppose this particular change. Hence, it is known as back EMF. And the back EMF is given by this particular equation. That is, EMF is equal to negative d phi by dt. In order to make it more smooth, we now know an equation for phi b. So we do know that phi is equal to L into I. For self-induction, this is the equation in order to find out the change in magnetic flux, or simply flux will be equal to self-inductance times the current that is flowing through that particular coil. So we can see that E will be equal to negative dLi divided by dt. So we do know that self-inductance is a constant. So we cannot directly differentiate that particular quantity, which means it gets kicked out. And we do know that current is the factor that is changing with respect to time, which means it is a changing quantity. So it remains inside that particular operator. So we can say that EMF E is equal to negative L di divided by dt. So this is the equation of EMF with self-inductance, or this is a relation that contains current, self-inductance and back EMF being produced. This negative sign indicates the direction of back EMF produced. So now we are going to find out what is the self-inductance of a solenoid. That is, we took the example of a solenoid and we derived, or we are going to derive, what is the expression for self-inductance for a solenoid. So first we need to write down what are the equations and what are the parameters considering this particular derivation. So we have a solenoid which has n number of turns, or simply n by L, that is number of turns per unit length indicated by small letter n, and there is I amount of current passing through that particular solenoid, and this particular solenoid has a length of L. So this particular solenoid is having current flow into this particular solenoid, which is changing the magnetic field associated with that, which is in turn producing the change in flux, which is in turn producing an EMF, and that is known as induction. So here we are going to calculate what is the value of self-induction, what are the relation or what are the quantities that will relate and give you self-induction. So we will start from the basic equation we know of self-induction, that is phi is equal to L into I. That is the first equation we know, that is phi is equal to Li. Now we do know that what is the equation for phi. So phi is equal to BA cos theta. Phi is equal to BA cos theta. And the change in magnetic field is being produced by the change in current, and hence it is resulting in the change in flux, which is producing the back EMF that we just discussed. And that is the reason why induction is happening here. It is just because of one coil, that is why it is known as self-induction. Now we can say that BA cos theta is equal to Li. Here it is not just BA cos theta. This is when there is only one turn, and here there are n number of turns. So we have to say it is NBA cos theta. Or here again we can substitute n as n is equal to small letter n into L. So we can write it as NL BA cos theta is equal to Li. Now again we are going to substitute one more result, that is what is the equation for magnetic field for a solenoid. So we already know that the equation for magnetic field strength, that is B for a solenoid is equal to mu naught into N into I. So we are going to substitute that, then we will get NL into mu naught Ni cos theta, which is equal to Li. There is an I on the left hand side, there is an I on the right hand side, we cancel that, and here we are going to consider theta. So theta is the angle between magnetic field and area vector A. So here we clearly know that both angles are in this particular direction, that is we are going to take it as 0 degrees because magnetic field lines are traveling in this particular direction, and the area vector, if I take the area of one particular loop, that particular area vector is also traveling in the same direction, which means the angle between them is 0, that is they are parallel to each other, hence theta will be here equal to 0 degrees. So I can write it as n square L cos theta into A. So there is an A here, so this will be equal to L, or simply rearranging and making it a little more sweet, retake, or simply rearranging it and making it a little more neat, we can say that n square, there is a mu naught here, so we can say n square mu naught L into A is equal to capital letter L. Here cos theta will be equal to 1 as theta is equal to 0 degrees. So we can have a relation, that is n square mu naught L times A will give you self-inductance. So this is the expression in order to find what is self-inductance. We can also write it in another way if you want, that is in order to do numericals also. We know that n by L is equal to n. So using this particular relation, we can also write it as L is equal to mu naught n square divided by L square into L into A. So we can say that L square and L cancels out. We can say that L is equal to mu naught n square A divided by L. This is one more way of representing the same equation, and we can generally say that the definition of self-inductance or the definition of self-inductance in a coil is defined as when current changes inside the coil 1 ampere per second, an EMF will be induced in that and that particular EMF will be equal to self-inductance. So even more clearly, we can say that when current in the coil changes 1 ampere per second, an EMF will be induced, and this will be self-inductance. Now the next topic is mutual induction. We just saw that if there is a coil like this, and if we change the amount of current passing through that, the coil itself will induce an EMF so that it opposes the relative change in this particular coil. So here the coil itself was inducing an EMF in order to prevent any change from happening. That particular EMF was known as back EMF. Now I am asking you that, is there any other way to produce this particular change? If I keep a coil right next to it like this, can I change the current in one coil so that it induces a change in the other coil? Is it even possible? So turns out it is actually possible. Now why is this actually possible? So we have to go to the fundamental principles. So what is actually producing this back EMF? That is, if I'm changing the current, what is happening? The magnetic field strength is changing. That particular change in magnetic field strength is producing a change in magnetic flux. That particular change in flux is the factor that is inducing this particular EMF. That particular change in flux is inducing that particular EMF, or simply the change in flux is causing induction to happen. So we only need a change in flux in order to produce the induction process that is required. So right now when I'm changing this particular current, what I'm actually varying is that the amount of field strength I'm varying. If I increase this particular current flow, then automatically fields will be penetrating the coil which is right next to that particular coil, which means I can say that if I am producing a change in one coil, or if I am changing the current that is traveling through one coil, the change in flux is actually affecting the other coil also, because at first the change in the first coil was actually zero. There was no magnetic fields penetrating that particular coil. But when I switched on the switch, when I increased the current, what happened? There was a magnetic field that was developed. That particular magnetic field is now penetrating the first coil. So there is a change in magnetic flux from 0 to maximum value. And if I switch this circuit off right now, there is again a change in magnetic flux, which will produce a back EMF. Understand this, as long as I'm using DC current, it is not like whenever I am passing a current through this particular coil, there is a back EMF being developed. No, there should be a change in current. It is very important to understand that the change in current or change in magnetic flux is the one that is producing the back EMF, or it is the factor that is inducing or producing induction process. If there is no change, if I'm using just a DC circuit, so if I'm using just a DC circuit like this, then the moment I turn it on and the moment I turn it off, then there will be the induction process happening. There will be a change in flux. In between, there won't be any change. But if I'm using an AC circuit, if I'm using alternating current which changes its direction constantly, then I can say that constantly there will be an induction process happening, a change in magnetic flux will be happening. But for now, just understand that it is the change in magnetic flux that is producing this particular EMF, or that is producing this particular induction. Here, if I turn it on instantly, the field in this particular coil was initially 0. When I turned it on, then there was field penetration through there, which is causing an EMF to be induced. So, even though this particular coil is not connected to anything, it is not connected to any electrical source, once I change the current passing through this particular coil, magically there is a EMF being induced in the other coil. So this particular induction of one coil which is affecting the other coil is known as mutual induction. That is, the change in magnetic flux associated with either one of this coil will produce an EMF in the other one. So it is affecting the other coil. So this is known as mutual induction. And this is the concept behind mutual induction. I hope you have understood that the change in magnetic flux linked with one coil is able to produce an EMF, that is, in the other coil, which is not even connected to any form of electrical power. So this particular phenomena is known as mutual induction. Vice versa is also possible. If the magnetic field associated with this coil is changing, an EMF is produced in the second coil. So both of these are happening simultaneously. That is the thing you have to understand here. Now mathematically we are going to prove that mutual induction is happening. And what are the properties of mutual induction? Mathematically we are going to find out a relation just like we did for self-induction. So again I'm briefing you the concept once again, that is, if I have two coils, there is coil 1 and coil 2, and if I'm allowing current to pass through any one of these coils. Let's say in coil 2, I'm allowing I2 current to pass. Since this is coil 2, the current passing through the coil 2 will be I2. So I2 amount of current is passing through the second coil, which means there is a flux being developed. So there is a flux which is developed inside this particular coil. So there is a flux being developed inside this particular coil 2. Now, this particular flux that is being produced by coil 2 is also passing through coil 1, which means there is a change in magnetic flux concentration, or magnetic field concentration is changing in coil 1 also. And since that particular magnetic flux associated with coil 1 is also changing, there is an EMF or voltage being induced in coil 1 also. So even though I am changing the current in the secondary coil, the primary coil is also having an EMF being induced in that. This is known as mutual inductance, or again we can say that this is dependent upon the amount of current passing through the coil. That is, if more amount of current is passing, more change will be there. That is, more change will be produced in flux. If lesser amount of current is passing, less change will be there for the flux. So we can actually derive the same derivation, that is, I is directly proportional to phi, or we can say that I into M is equal to phi. Here M is known as mutual inductance. There it was L because it is self-inductance. One coil is producing EMF within itself. Here one coil is producing EMF on another coil because of its influence. So that is known as mutual inductance. This M is a constant known as mutual inductance. So again, just as for the self-inductance case, we are going to derive a relation between mutual inductance and the quantities that is relating here. So first we are going to write down, that is, phi is equal to Mi. Here it is M because it is mutual inductance. So phi is equal to Mi. Here now we are going to specify, is it because of the first coil? Is it because of the second coil? So we are going to specify it using numbers. So here I am going to consider the flux change in the primary coil due to the current that is flowing through the secondary coil. So there are n number of turns and the flux is changing in the primary coil. So n number of turns in coil 1 and the flux associated with the primary coil is changing because of the current that is changing in the secondary coil. Or we can clearly say that because of the current that is flowing through the secondary coil, the primary coil is experiencing a change in magnetic flux. So I2 is producing a change in the flux of primary coil. So I2 is producing change in phi 1. Now we are going to write it again just like we did it for the self-induction case. That is, even though n is the number of turns, n by L will be equal to small n, that is, n is equal to NL. We are going to substitute this one. So we can say, so this is the length. So we can say that NL phi will be written as BA cos theta, which is equal to M I2. Here, which B is producing the change? Is it B1? Is it B2? That is, the magnetic field is associated to which coil? So we do know that magnetic field is associated to coil number 2 because current is passing through coil number 2 and that particular coil is the one that is producing the magnetic field. That particular magnetic field is changing. So we can see that it is B2. So we can say that it is B2 and here it is N1 because we are counting or we are considering coil 1's flux change. So the flux change in coil 1, we are writing it down as N1. L is same because both the coils have the same length, roughly the same length. So I am taking it as L itself. So N1 into L into B2 because the magnetic field which is changing is associated with the secondary coil. So B2 into A. A is common for both. Again, why? Because A is the area vector. Here we know that the area vector of coil 1 and coil 2 are both in the same direction. So we can take A as general. So we can say B2 into A into cos theta. Cos theta is again the angle between magnetic field lines and area vector. Again, cos theta will be equal to 0 degrees, which means cos theta will be equal to 1 as theta is equal to 0 degrees. So we can write it down again as N1 L into B2 into A will be equal to MI2. That is, I2 current flowing in the secondary coil is producing a change in flux in the primary coil. That particular change in flux is produced by the change in magnetic field on the secondary coil. That much is clear, I hope. Now we are going to substitute the value of B in this particular equation. We already know B for a solenoid is N1 L into B. B is nothing but N into mu naught Ni. So N, that is B is equal to mu naught Ni. Here it is N2, that is we are considering coil number 2. So it is coil number 2 and current is I2. So we can say it is N2 mu naught I2 into A is equal to MI2. So here we can rewrite this equation. We first cancel out the I2 and I2. So we can write it as N1 into N2 into L into mu naught A is equal to M. So this is the first relation we have obtained. That is magnetic retake. That is mutual induction is given or related to this particular coil through this particular formula. N1, N2 into L into mu naught times A will give you mutual induction. Now, who is inducing this current onto whom? So, who is being induced here? Mutual induction. So, here we can say that the primary coil is being induced by the secondary coil. So, we can clearly say that the primary coil is being induced by the secondary coil. So, primary coil is being induced by the secondary coil. So, we can include M12. So, it is just to clarify who is under the influence of whom. So, is coil 1 under the influence of coil 2? Coil 2 is under the influence of coil 1. Just to specify that, we use this particular numbering system. It is basically very simple. So, flux is directly proportional to current. Since flux change is being produced by two coils, we are going to consider mutual inductance as the constant. So, we can write it as the flux change in primary coil is because of the current in the secondary coil. We named it and we expanded that particular equation, rearranged it so that we have a definition for mutual induction. Now, it is not just done yet. This is when current is being changed in the secondary coil. Now, will the same happen if I change the current for the primary coil? Of course, because both of them are passing through the bulb. Again, if magnetic field is changing to either one of these coils, they can mutually induce a current. That is the whole point of the concept. But again, we have to mathematically prove that. So the same thing will happen with only a few minor changes. So instead of having current I2 passing through coil 2, now I am saying that there is no current passing through coil 2 and there is only current passing through coil 1. If there is only current passing through coil 1, then the magnetic field is producing or inducing an EMF on coil number 2. So we can write it as N2, that is N2 phi 2 will be equal to M21 into I1. That is, current in the first coil or current through the primary coil is inducing a change in flux in the secondary coil. And so second coil is inducing a change in the primary coil, that is M21. So current in the first coil is inducing a change in flux in the secondary coil. Now the same things, we are just expanding that. So we are just expanding. N is written as N into L. So N2 into L. Phi is written down as B1. That is, here it was because of secondary coil's magnetic field strength. Here it is because of primary coil's magnetic field strength. So B1 into A into cos theta will be equal to M21 into I1. Now again, N2 into L, B1 is again written down as mu naught into N into I. So it is written down as mu naught into N1 because of magnetic field 1. So N1 mu naught into N into I1 into A. Cos theta, again the angle between area vector and the magnetic field lines is again theta is equal to 0 degrees. So theta is equal to 0 degrees, which means cos theta will be equal to 1. So we can write it down just as A, because it is A into 1. So N2 into L into mu naught into N1 into I1 into A will be equal to M21 into I1. The I1 and I1 will cancel each other out. So we can write it down as M21 will be equal to N1 into N2 into mu naught into L into A. The whole point about this equation is that change in one coil is inducing a magnetic flux change, or simply the change in magnetic flux in one coil is producing an EMF on the other coil, and vice versa. That is, if I change flux in one coil, the secondary coil is producing the EMF. If I change the current associated with the second coil, then the flux change is in, or simply the flux change or EMF being produced is also in the primary coil. So mutually they are inducing each other. So if you look at these two equations, it is N1, N2, N1, N2, mu naught, L into A, which means we can say that M12 is equal to M21. That is the whole point. That is, change in any one of the coil, that is current change or flux change linked with any one of the coil can induce a change in the other one. That is the whole point of this particular derivation. I hope you have understood everything about mutual induction's derivation, because this is really important. Now, just like we found the back EMF produced for the self-inductance, we also have to find out what is the back EMF produced for mutual inductance. The same principle, that is E is equal to negative d phi divided by dt. So here it is E is equal to negative d m into I divided by dt, or simply we can say it is equal to, that is EMF is equal to negative m di divided by dt. We can define mutual inductance as the EMF induced in one coil when current is changed 1 ampere per second in the other coil. That is, if I have two coils like this, if I if I change, let's say current is flowing through this primary coil, that is I. If I change the current flowing through this primary coil 1 ampere per second, there will be automatically an EMF induced in the other coil. That particular EMF is known as mutual inductance, or it is a definition of mutual inductance. They can ask it for 1 marks. That is, it is very easy to define, even if it is mutual inductance or self-inductance. The only thing you have to do is put 1 ampere here and 1 EMF here. That is 1 volt here. Then you will have the definition for mutual inductance or self-inductance. Both have almost similar meaning and definition. So I hope you have understood everything about induction, self-inductance, mutual inductance, and the way we found a relation between mutual inductance. That is because of coil 1 and coil 2. Basically, they both are same. So inductance is nothing but the process of opposing a relative change by producing an EMF against that. That is, if we increase or decrease a current, then an EMF will be produced in order to oppose that particular change. We saw that as a consequence of Lenz's law. So that particular principle is taken a step further and we are defining it as inductance. And without inductance, many of the things we see won't happen. For example, mutual inductance is actually used in transformers, which we will see very shortly. So I hope you have understood everything about self-induction and mutual induction. I'll see you in the very next class with a new topic. Thank you.